We're going to take a look at the three-dimensional coordinate system. Very important because we'll be doing most of our work in Calculus 3 in three dimensions. Almost everything we do in Calc 3 will be in that three-dimensional space. A lot of what we do anyway. Um, well, instead of a coordinate plane, the XY coordinate plane, we're going to have three coordinate axes, the X, Y, Z coordinate axes. I'm going to draw mine this way almost every time. And so the way you want to think about this, when I draw my coordinate axes, and the way they're printed in most books as well, you have the YZ plane that's sort of on the screen, and then the x-axis is coming out of the screen. And so you can think about the x-axis coming straight out of the screen, and then the negative x-axis would be going back in to the screen here. Negative z would be going down, negative y would be going off to the left, the way we have things oriented. And you can draw it different ways. What you have to remember is what we refer to as the right hand rule, which says this: if you take the fingers of your right hand and curl them from the x-axis to the y-axis, your thumb should be pointing in the direction of the positive z-axis. So with that in mind, I could draw my coordinate axes a different way and still have them be correct. For example, we could have, say, x going up, y coming out of the screen, and z going to the right, positive z going to the right. And we still have the right hand rule here, because as I would curl the fingers of my right hand, think about that, from the x to the y-axis, my thumb would be pointing in the positive z direction. So there's more than one way to draw the three-dimensional coordinate axis system, but the one we're going to be using almost exclusively is this orientation right here. So with that in mind, then, we can think about having three coordinate planes, and we basically have, well, let's start actually with the one we are familiar with, the xy plane. So that's the plane that's formed by just considering points that are on that xy plane. So I'm trying to sketch that out here. Here is an idea of where that xy plane lies. And of course, if we're on the xy plane, then our z coordinate is going to be 0. We have an x coordinate and a y coordinate that could be non-zero, but z would have to be non-zero. Now I can also consider the xz plane. So that's the plane that is formed by the x and z axes. So that would be the one sort of coming out of the screen like so, and back like that. All right, there's my xz plane. Of course, if I'm on the xz plane, then my y value is going to be 0. And finally, we can consider then the yz plane. And if I'm on the yz plane, then of course the x value is going to be 0. The way I have it drawn here, the yz plane is just the plane that is, well, in this case, the screen, or the piece of paper that you're drawing on, whatever it happens to be. Usually the YZ plane is the flat plane that we're drawing on, thinking about the x-axis as coming out of that. So we have what we call those three coordinate planes, and in addition to those, we have 8 octants. So where everything is positive, we have octant 1. So where x, y, and z are all positive, that's octant 1. And then I'm not going to try and draw in here, it'll just get too messy, but as we move around the way we normally do in the xy plane, we go to 2. So there, x is negative, y is positive, and z is positive. 3 is where x is negative, y is negative, and z is positive. Octant 4, y is negative, x is positive, z is positive. And then around the same way, where z is negative, 5, 6, 7, both y and x are negative along with z. And then 8, x is positive, y is negative, z is negative. So those are our 8 octants to go with those three coordinate planes in our three-dimensional coordinate system. Now, this seems like maybe an obvious statement here, but it's an important statement nonetheless. When we talk about three-dimensional space, what we're talking about then is a way that we can actually, well, we can assign values to every point in that three-dimensional space, and that's very important. So the way we would say it is this: the three-dimensional space is in what we call one-to-one correspondence with what we refer to as R3. You may have heard the XY coordinate plane referred to as R2 sometimes, and you can think of this as R cross R cross R. Now what does that equal to? In set notation, this is a set of instead of ordered pairs, we have ordered triples. All ordered triples, X, Y, Z. We're going to make sure that those are all real numbers. X, Y, and Z are all real numbers. And again, we call that the set of ordered triples. So put it very simply, if you give me a point such as, oh, I don't know, 2, 3, 5, that can be plotted to a specific spot in, well, we'll say in three-dimensional space, 3D space. And conversely, every point in that three-dimensional space is associated with a unique ordered triple. So again, it may seem like kind of an obvious statement, but it is an important statement. If you give me an ordered triple, 3 numbers, we can put that in a very specific spot in 3 space, in three-dimensional space, in R3. And if you give me a particular point in three-dimensional space, assuming we have a coordinate system associated with that, then we can say that that belongs to a, or we can call that a very specific ordered triple. So, for example, let's just plot a couple of points here, and it's a little bit tricky. It's not hard. We'll plot maybe that point 2, 3, 5, and then, oh, maybe we'll also plot the point -2, -1, and 4. It's just sometimes hard to draw things in three-dimensional space, but get a little better at it. Luckily for you guys, I've taught Calc 3 a couple of times, so I'm not as bad as I once was in drawing things in 3 dimensions. So let's take a look at this first point, 2, 3, 5. So we're going to come out 2 on the positive x-axis. Always x, then y, then z. That's why we call them an ordered triple. The order matters. 3 on the y, 5 on the z. So starting at the origin then, I'm going to come out 2 on the x. I'm going to go 3 on the y. So what I'm going to form here basically is couple of parallelograms, and then actually form what's called a parallelepiped, sort of a three-dimensional parallelogram. And here's our point, 2, 3, 5. So I went out 2 on the x, over 3 on the y, and then up 5 on the z, and that's where I end up in 3 space. Now this one might be a little bit more difficult. -2, -1, +4. So here I'm going to go back 2 on the x-axis. So I have to go, thinking this is our negative x-axis going into the screen, I'm going to go back 2 to the left 1 on the y-axis, and then up 4. So let's see if I can get there from here. I'm going to go back 2 to the left 1, so let's form a little box there, and then up 4. So I'm going to go up from this spot. I'm going to do the same thing. So let's see, back 2, back 2 to the left 1. Yeah, it's kind of a difficult thing, but this is going to be our spot. Let me put it in orange here, somewhere in there. So back 2 to the left 1 and up 4. So again, that's not a very good spot, is it? Because it shouldn't have the same height as the other one. The other one was only at height 5. Let me see if I can back that up just a bit, and maybe take that down a notch. I don't mean to get too involved in this. You're not going to be asked to plot a lot of points, but something like this. So maybe about right here is the point -2, -1, 4. All right, enough plotting. Let's get on to more interesting things, and that is drawing some graphs of things in R3. Let's suppose that we were asked to graph a couple of things. Let's start with this equation, y equals 2. Well, if I want you to graph this, I have to tell you, first of all, where I want you to graph it. For example, if I want you to graph it in R2, which, before you got into Calc 3, before today, really, is what you would assume, that we're going to graph things in R2, you'd say, oh, y equals 2, well, I know what that is. That's, let's see, x and y. That's up 2 on the y-axis, y is 2, x can be anything we want it to be, and so that's just this horizontal line, y equals 2. And you'd be exactly right, but in R3, my friends, it's a different story. If I ask you to graph this in R3 in three-dimensional space, well, now y still has to be 2, so we're going to go out 2 on the positive y-axis. But not only can x be anything, but z can be anything. And so if I label my axes correctly, this would be z right here, what we end up with is, instead of a line in R2, we're going to have a plane in R3. So lines in R2 translate into planes in R3, and we'll see more examples of that. But it's basically just a plane that is cutting through the y-axis at y equals 2, it's parallel, we could say that, parallel to the xz coordinate plane. And so any point on this plane is going to have a y-coordinate of 2. The x and z values rather, will vary. Let's try another graph while we're on a roll. How about we want to sketch the graph y equals x squared? You say, all right, well, how many dimensions? You want me to sketch it in R2? That's no problem, because in R2, all you've got is a parabola. Of course, y equals x squared is just a parabola. Opening up on the y-axis. But if I say, no, I don't want you to sketch that in R2, I want you to sketch that in R3. So we have to extend it a dimension, drawing our coordinate axes in R3 the way we normally do. X, y, and z, x coming out of the screen. I'm going to start by drawing that same parabola in the xy plane. That's this plane that's sort of laying flat here and coming out of the screen. So I'm just going to retrace that parabola. And of course that extends infinitely far up the positive y-axis. But now z can be anything as well. So what we end up with then is this thing extending up infinitely far in the z direction, both positive and negative. And we call that a parabolic cylinder. We have a three-dimensional surface in R3. We call this a parabolic cylinder. That's kind of cool, huh? Hope you can see what I'm trying to convey there.